Welcome to our final project. My name is Eddie and my partner is Emiliano. Today we're going to be talking about linear algebra. Now you might be asking, what is linear algebra? To keep it brief, linear algebra is the branch of mathematics that deals with vectors, matrices, and linear transformations. It's a great learning tool when it comes to understanding and solving systems of linear equations as well. And it has many applications in science and engineering. You can find linear algebra in physics, computer graphics, machine learning, data science, and many other fields.
The topic discussion for our presentation is Cramer's rule, and the reason we decided on this is because we wanted to see if we could fully explain a whole new idea to others and just find a new way to solve linear systems compared to the ways we've learned it throughout the course. And furthermore, the name Cramer was just very funny, and we didn't know what that meant in correlation to linear algebra. So the idea of Cramer's rule is connected to the determinant section of the textbook in chapter 3, specifically 3.3 when we were introduced to determinants, I'm pretty sure. And in simple terms, Cramer's rule is simply a different way to solve linear systems, but using determinants to solve it. The matrix must be invertible in order to be performed using Cramer's rule. So the first steps of Cramer's rule involves the idea of determinant A not being 0, which, if true, leads to xi for each variable b in xi equals determinant A b over determinant A, with I being 1, 2, and it keeps going. And yeah, just basically any number being n. And then this showcases how ax equals b is related and leads to the multiplication property of determinants, which is determinant A and determinant Lix equals determinant AI B, a bunch of stuff. And then after this, cofactor expansion is done and creates determinant Xi equals determinant AI B, which proves that the matrix is invertible. So basically all that stuff was just showcasing that determinant is invertible. And it views the system as ax equals b, and with the notation of the determinant, a linear system can be solved. So an example of this would be from the textbook specifically, where it showcases the system 3x1 minus 2x2 equals 6, and then negative 5x1 plus 4x2 equals 8. And the matrix of A would be 3, negative 5, negative 2, and 4. And then the matrix of A1B is 6, 8, and negative 2, 4. And then the matrix of A2B is 3, negative 5, 6, and 8. And then in order to compute this, we got to find the determinant of A for each of those specific ones. So to find determinant A, you have to do 3 times 4 minus negative 5 times negative 2, which is 2. And when you do 12 minus 10, that's the result. And then because the determinant is not 0, the solution is unique, and Cramer's rule can be applied as a result. And the next step is to form the matrices and replace the columns of A with the vector of B, that is 6, 8. So A1 is now 6, 8, and negative 2, 4, and A2 is 3, negative 5, 6, 8. And so after this, the computation of the determinants for both A1 and A2 is done to figure out the determinants for each of them. And so the determinant of the A1 matrix is 6 times 4 minus negative 2 times 8, which is 40. And then the determinant for A2 is 3 times 8 minus negative 5 times 6, which is 54. And then with these determinants, the Cramer's rule is finally applied, and x1 and x2 are found with the formula of determinant AI over determinant A, with determinant A1 over determinant A, and determinant A2 over determinant A. Basically, you're just taking each of the two matrices that we just found out, which was A1 and A2, and then just have them divided by the original determinant. Just a bunch of determinants just throughout is what I've learned. And then you simply just do 40 divided by 2, which is 20, and then 54 divided by 2 is 27, which leads to x1 being 20, and x2 being 27, and that is the result. It isn't that long, trust me, it's very hard for me to articulate it in some sense, if you couldn't tell. And so it involved a lot of determinants being solved, but it led to the result of this linear system that we ultimately were trying to find. And despite being a one-and-done rule for a linear system, it also heavily relies on the idea of invertibility for a matrix, which was discussed through the course. and configuring a determinant, which was implemented a lot through this and just throughout the course as well. If the determinant was not zero, Cramer's rule could not be applied, but if it was not, it indicates that it was not invertible. It was linearly independent, and that Cramer's rule is not applicable because there is no unique solution. And so after going through the process of Cramer's rule, we both can see why this may not have been that priority in this class, because quite frankly, it was just a one and done way to figure out a linear system and didn't really seem as important compared to the other topics discussed. But it's still an interesting way to solve it, and just seeing, in my opinion, just seeing how something as not minuscule, I don't want to say minuscule, but not as important, still connect through the entire course. That was because that's a main thing throughout the course, where every single topic that we discuss connects with each other. I just found that interesting. And an extra detail when going through this rule is just, I just wanted to know what Cramer even meant. And of course, it was obviously the name of the creator of this rule, Gabriel Cramer. And he was the first to discover the idea of solving a system of linear equations with determinants. And so to summarize, Cramer's rule is a good method that is simple and precise when solving linear systems, especially many equations that involve multiple variables. It must reflect on the smaller parts of linear algebra and how the small lessons not covered still connect through the idea of linear algebra that provides a bigger picture as a whole. I hopefully didn't miss anything. And yeah, that's it. Thank you for watching.